Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the examples on sylllow theory. Now see here examples. A group of order 255 must have either 1 or 85 sylllow 3 subgroups. Solutions 255 is equal to 3 multiply 5 multiply 17. Let R denote the number of sylllow 3 subgroups. Therefore, R divides coordinate of G. Therefore, R divides 255, where R is equal to 1, 3, 5, 15, 17, 51, 85, 255. R is equal to 1 modulus of 3, that is 3 divides R minus 1. Therefore, R is equal to 1 or 85. Next example, if coordinate of G is equal to 45, then prove that G contains only one sylllow 3 subgroups. Solutions. Coordinate of G is equal to 45 is equal to 3 square multiplied pi. By first sylllow theorem, G contains only 3 subgroups, each of order 3 square is equal to 9. Let R is equal to number of sylllow 3 subgroups in G. By third sylllow theorem, R divides coordinate of G. Therefore, R is congruent to 1 modulus of 3. Hence, R divides coordinate of G. Therefore, R divides 45. R belongs to 1, 3, 5, 9, 15, 45. Therefore, R is congruent to 1 modulus of 3. Therefore, R is equal to 1. This shows that there exists only one sylllow 3 subgroup of order 3 square is equal to 9. Say H. By second sylllow theorem, H is equal to G inverse Hg for any G belongs to G. Hence, H is a proper normal subgroup of G. Hence, G is not simple. Show that a group of order 255 is not simple. Let G be a group of order 255. Coordinate of G is equal to 255. Coordinate of G is equal to 17 multiply 5 multiply 3 is equal to 17 multiply 15, and 17 does not divide 15. By first sylllow theorem, there exists sylllow 17 subgroup in G, each of order 17. Let R number of sylllow 17 subgroups. Then by third sylllow theorem, R divides coordinate of G. R is congruent to 1 modulus of 17. Hence, R divides coordinate of G. R belongs to 1, 3, 5, 15, 16, 17, 51, 85 and 255. R is congruent to 1 modulus of 17. Therefore, R is equal to 1. Thus, there exists only one sylllow 17 subgroup in G by H. Then by second sylllow theorem, H must be normal in G. That is, coordinate of H is equal to 17. H is a proper normal subgroup of G. Hence, G is not simple. Show that no group of order 30 is simple. Let G be a group with the coordinate of G, order of G is equal to 30 is equal to 5 multiply 3 multiply 2. By fourth sylllow theorem, G contains sylllow 5 subgroup, each of order 5. Let R be number of sylllow 5 subgroup of G. Then by third sylllow theorem, R divides coordinate of G. R is congruent to 1 modulus of 5. Hence, R divides coordinate of G is equal to 30. R belongs to 1, 2, 3, 5, 7, 6, 10, 15, 30. R is congruent to 1 modulus of 5. 5 does not divides R minus 1. Hence, R is equal to 1 or 6. Suppose G contains 6 sylllow 5 subgroups. Let they be H1, H2, H3 H5 and H6 be distinct sylllow 5 subgroups. Then order of HI is equal to 5 for 1 less equal I less equal 6. HI intersection Hj is equal to singleton if for I is not equal to j. If X belongs to HI intersection Hj and if X is not equal to E, then singleton X is equal to HI is equal to Hj. Hence, for each HI contains 4 elements, each of order 5. Hence, there exists 6 multiply 4 is equal to 24 element in G, each of order 5. Therefore, G of order 30 is not simple. By second, fourth sylllow theorem, G contains sylllow 3 subgroup, each of order 3. Let R is equal to number of sylllow 3 subgroup of G. Then by third sylllow theorem, R divides coordinate of G and R is equal to 1 modulus of 3. Hence, R divides coordinate of G is equal to 30. R belongs to 1, 2, 3, 5, 6, 10, 15, 30. Therefore, R is equal to 1 modulus of 3. 3 divides R minus 1. Hence, R is equal to 1 or 13. Suppose G contains 10 sylllow 3 subgroups, each of order 3. Let K1, K2 K10 denotes distinct sylllow 3 subgroup of G. As we can prove, the G contains 20 distinct elements, each of order 3. Thus, from first and second, if G contains 6 sylllow 5 subgroups and 10 sylllow 3 subgroups, then G must contains 24 plus 20 is equal to 40 distinct element, which is not true as coordinate of G is equal to 30. Hence, G must contains either only one sylllow 5 subgroups are only one sylllow three subgroups. Thus, in either the case, G contains a proper normal subgroup by second sylllow theorem. Hence, G is not simple. Hence, G is not simple. No order, no group of order. Prove that no group of order 36 is simple. Let G be a group with coordinate of G is equal to 36. Coordinate of G is equal to 36 is equal to 3 square multiply 2 square is equal to, and 3 not divides 4. But by fourth sylllow theorem, G contains sylllow 3 subgroup each of order 9. Let R the number of sylllow 3 subgroup of G. Then by third sylllow theorem, R divides coordinate of G and R is equal congruent to 1 modulus of 3. Hence, R is divides coordinate of G is equal to 36. And R is equal to 1 modulus of 3. 3 divides R minus 1. Hence, R is equal to 1 or 4. Suppose G contains 4 sylllow 3 subgroups of order 9. Let H, K be any two distinct sylllow 3 subgroups. Then coordinate of H is equal to 9 and coordinate of K is equal to 9. Coordinate of HK is equal to coordinate of H multiply coordinate of K divided by coordinate of H intersection K. Hence, HK is a subset of G implies that coordinate of H intersection K is equal to 3. H intersection K is a subgroup of H. Order of H intersection K divides order of H. Order of H intersection K divides 9. Order of H intersection K belongs to 139. Order of H intersection K is equal to 1. Order of coordinate of HK is equal to 81, which is impossible. Therefore, an order of H intersection K is equal to 9. Therefore, H is equal to K, which is not true. Consider the intergroup of n of H intersection K. 3 divides order of H intersection K. H intersection K subgroup of n of H intersection K, and hence n of H intersection K belongs to 1836. N of H intersection K divides order coordinate of G is equal to 36. If coordinate of H intersection K or n of H intersection K is equal to 18, then index of n of H intersection K is in G is 2. Then n of H intersection K is a proper normal subgroup G, proving that G is not simple. If n of H intersection K is equal to 36, then n of H intersection K is equal to G. In this case, H intersection K will be a proper normal subgroup of G. Hence, G is not simple in either the case, and which is required proof.